Welcome to NGVEX Explainer.
Welcome to the Explainer. You know, if you've ever found yourself just staring at a massive wall of 3D printer filaments, or maybe endlessly scrolling through online stores wondering what on earth the actual difference is between PLA, PETG, Nylon, and, say, aerospace-grade PEEK, well, you are in exactly the right place. Today, we're completely demystifying this incredibly complex and honestly sometimes just confusing filament landscape. Okay, let's dive into this.
We are going on a bit of a categorical journey today. We'll be looking at 1. The everyday essentials. 2. Functional workhorses. 3. Tough and flexible. 4. Composites and specialty. And finally, 5. Extreme ultra polymers. Basically, we're starting from your basic desktop printing and scaling all the way up to the extreme stuff.
All right, kicking things off with Tier 1, the everyday essentials.
This is the baseline tier where almost everyone starts their 3D printing journey. And right at the heart of it is PLA, or polylactic acid. It's actually derived from renewable resources like cornstarch and sugarcane, which is cool because that makes it biodegradable. It is absolutely the king of easy printing. You get minimal warping, really crisp dimensional accuracy, and just a massive selection of colors. But, and this is a pretty big but, it has a fatal flaw. PLA is extremely brittle, and its glass transition temperature, basically the point where it goes from a hard plastic to soft and droopy, is really low, like around 50 to 60 degrees Celsius. So if you leave a PLA part in a hot car during the summer, yeah, it is going to warp and completely deform. Because of that, it's really best reserved for concept models, visual prototypes, and just indoor jigs.
Now, material scientists totally knew PLA was brittle, right? So they created PLA+, sometimes called tough PLA. So the crucial point is that these modified blends sacrifice just a tiny bit of raw stiffness to give you a whole lot more real-world handling durability. If you're printing snap-fit features, clips, or just parts that are definitely going to get bumped and handled around the house, PLA Plus is your go-to. It basically gives you the printing ease of PLA, but with significantly fewer of those annoying brittle failures.
Moving right along, we have Tier 2, functional workhorses. This is where we step up to prints that need to survive real mechanical load, heat, or live outdoors. Meet PEG. This is pretty much your default do-everything functional material. Think of it as combining the printing ease of PLA with the functional durability of ABS. Its glass transition jumps up to around 80 degrees Celsius, so it definitely holds heat much better. And unlike PLA, which just abruptly snaps under heavy stress, PETG is semi-flexible. It bends before it breaks. Add in its excellent chemical and moisture resistance, and you have the absolute perfect material for structural brackets, protective cases, and even fluid containers.
For higher heat and impact resistance, engineers have traditionally turned to ABS. That's the exact same plastic Lego bricks are made out of. ABS gives you that classic toughness, 100-degree heat resistance, and you can even vapor smooth it with acetone for a glossy finish. But ABS has a massive weakness. It degrades, turns yellow, and gets super brittle under UV exposure from the sun. So, enter ASA. ASA is essentially an upgraded ABS designed specifically for the outdoors. By swapping out its UV-sensitive rubber components for a stable acrylic ester, ASA gains literally perfect weather stability. The takeaway here, if your part is going outside, skip the ABS and just print it in ASA.
Let's move to and see how this builds in terms of hardware requirements, because you really can't just throw high-performance materials at a basic entry-level printer. Notice the progression here. PLA needs minimal heat and no enclosure. PETG steps up those temperatures, so you definitely need a hotbed. But once you hit ABS and ASA, you're looking at nozzle temps up to 260 degrees, beds well over 100 degrees, and you absolutely must have a heated, ventilated enclosure. That's crucial to prevent aggressive warping and to safely manage the fumes.
Assuming you've got the hardware sorted, we can step into Tier 3, tough and flexible.
This is the tier where materials solve very specific physical problems, like friction, repeated bending, and high-impact strikes. And this brilliantly illustrates the difference in behavior here. See, rigid materials take a lot of stress, but then they just yield and snap very quickly. But elastomeric materials, like TPU, have a low modulus. That means they are soft, but their elongation is absolutely incredible. A printed sample of TPU can stretch up to 4.5 times its original length before breaking. That's just wild.
For raw toughness, the absolute standout here is nylon, which you'll often see labeled as PA6 or PA12. Nylon is the ultimate engineering choice for parts that need to slide, rub, or flex repeatedly without failing. What makes it genuinely unique in this category is that it's self-lubricating. So if you're printing functional gears, living hinges, or snap-fit connectors, nylon is unmatched. Just one major thing to remember, it absorbs moisture like a sponge. You absolutely must aggressively dry it before and even during your printing.
Then we have the true elastomers, TPU and TPE. These give you real rubber-like flexibility, which is usually measured on what's called the Shore hardness scale instead of standard rigid tests. TPU is essentially your definitive shock absorber and gasket maker. It doesn't just bend, it absorbs heavy impacts that would completely shatter rigid plastics. The trade-off, though, because it is literally like trying to push a wet noodle through a tiny tube, it's pretty tricky to feed through standard extruders. You really have to print this stuff incredibly slowly.
Next up, we transition into Tier 4, Composites and Specialty.
This is a fascinating realm where standard plastics get a massive mechanical or functional upgrade by mixing in specialized fibers. A perfect example of this is comparing standard PETG to carbon fiber PETG, or CFPETG. Standard PETG is great, as we discussed, but it does have that slight flex. By adding chopped carbon fiber right into the polymer matrix, that flex is entirely eliminated. CFPETG is incredibly stiff, entirely unyielding, and offers superior dimensional accuracy because those fibers actually prevent the plastic from shrinking as it cools. It's the absolute perfect choice for rigid drone frames or high-stress robotic arms. Just be warned, carbon fiber is highly abrasive. It will literally destroy a standard brass nozzle in a single print, so swapping to a hardened steel nozzle is absolutely mandatory.
But composites add more than just strength, they add function. Take conductive PLA, for instance. It's filled with conductive materials, allowing you to literally print low-voltage circuits or capacitive touch sensors right into your solid models. And then we have support materials. If you're lucky enough to have a dual extrusion printer, you can print your main object in one material and all the supports in PVA. PVA dissolves completely in plain water. Or you can use HIPS, which dissolves in a chemical called limonene. This is a total game changer because it enables incredibly complex internal geometries and moving parts that are printed completely assembled right on the build plate.
And finally, we reach the summit, Tier 5, Extreme Ultra Polymers.
We are now talking about materials designed to literally replace metal in demanding industrial, medical, and aerospace fields. We start this extreme tier with polycarbonate and PEI, which is also known by the brand name Ultem. Polycarbonate offers immense heat deflection and shear strength, but PEI is truly special for heavy manufacturing. It has an amorphous randomized molecular structure. Unlike orderly crystalline materials, this means it doesn't dramatically shrink and warp as it cools down. Provided you have a highly controlled, high-temperature printer, and we're talking serious chamber temps of like 120 degrees Celsius here, PEI allows for massive, structurally stable prints that simply will not warp.
At the very top of the material food chain, we have the PEEK family, PEEK and PEC. Now, what's really interesting about this slide is the fascinating nuance between these two aerospace heavyweights. PEEK has the highest raw tensile strength and is fantastic for high-volume structural parts, but PEC has an extra ketone group in its molecular chain. What that means is it crystallizes slower. For 3D printing specifically, slower crystallization gives the printed layers more time to fuse together, which results in much superior layer adhesion. PEC also offers unbelievable flame, smoke, and toxicity compliance, making it highly sought after for aerospace interiors.
If you really want to see how far the technology has come, just look at this jump in raw strength. Standard PLA has a tensile strength of around 50 megapascals. Standard PEEK doubles that, to about 100 megapascals. But when you reinforce PEEK with continuous carbon fiber, the tensile strength jumps to a jaw-dropping 212 megapascals. At this point, we are completely blurring the line between plastic and metal, which allows for extreme lightweighting in automotive and aerospace applications.
And you know, it's not just about physical strength either. These advanced filaments don't just hold weight, they resist nearly everything you can throw at them. Materials like polypropylene, PETG, and especially the ultrapolymers like PEEK boast incredible resistance across the board against harsh acids, strong bases, and intense industrial solvents.
So, to wrap this all up into something actionable, here is your progressive material selection blueprint. The golden rule here is never over-engineer your project if you don't have to. Step 1. Always start with PLA for fast prototyping, visual models, and just checking your fit and form. Step 2. Upgrade the PETG when you actually need standard indoor functional load bearing. Step 3. If the part will ever see sunlight, switch directly to ASA for that sweet UV resistance. Step 4. When dealing with specialized physics like bending, wearing, or impact, utilize TPU or Nylon. And finally, Step 5. Reserve the costly composites and ultrapolymers for when your part faces extreme thermal, chemical, or structural stress.
The evolution of 3D printing filaments has taken us from printing simple desktop trinkets all the way to fabricating rocket and aerospace components right in our own workshops.
It is truly incredible how accessible these industrial-grade materials have become for all of us. So, armed with this material knowledge, I want to leave you with this question. What limits are you going to push with your next functional print? Thanks so much for joining me on this explainer.
If you enjoyed this video, don't forget to like, subscribe, and turn on the notification bell so you never miss our latest engineering explainers. Thanks for watching, and I'll see you in the next video.